Recording is rolling. It is Tuesday, October 1st. So you guys have your projectile quizzes back. So on there was really only one question that looked like students were pretty universally struggling on. That was number 6. That was there was a tall cliff and a short cliff. So I'm gonna go over that one with you guys. You guys remember Monday and then back to Friday we were doing some Atwood labs. So I got a warm up question here. We'll go figure out the okay, 2 questions really, right? So here's a classic Atwood, like you guys were doing yesterday. Right, and then after that, switch over, look at chapter 4 puzzles. I did finish writing your dynamics quiz last night, so I'm going to get that to you guys on Thursday. So here's upcoming due dates. Let's just have it all due on Monday. Your guys' chapter 4 puzzles and the quiz that I'll eventually get to you guys by the end of Thursday. So that let's have a Monday. All right, you guys can turn that all in on Monday. All right. Speaking of AP classroom, here, guys, focus here. All right. So, no due date on that yet because actually, all right. So AP reorganized the whole class over the summer, so they shuffled a bunch of topics around. In Unit 2, actually everything we've been doing for the past 2 or 3 weeks now has been in like used to be Unit 2, which is just dynamics, force, Newton's laws of motion, that sort of thing. Okay? The new Unit 2 is all that, and also they threw in like some rotational motion, some centripetal force kind of stuff. So yeah, but we haven't talked about everything that's on the new Unit 2 yet, so hang tight on that. Okay. Yeah. If you have test corrections for linear motion, you can still turn those in. I know we're getting pretty close to the end of the 9 weeks. I think at the end of the 9 weeks, I won't be able to change grades then, or it'd be like really hard to. I have to like talk to guidance and stuff, and sometimes they don't allow me to. Right, but yeah, anything up to 9 weeks. If you guys have anything, turn it in. Projectile corrections. If you want to do corrections on projectile quiz, you can do that too. Yeah, I think for the most part, you guys are good on these, except for number 6, which I'll do right now with you guys. All right, so here we go. Let's switch over to projectile quiz number 6. Let's take a good look at here. It says a ball launcher launches the ball horizontally off a cliff, height h. The ball lands some distance x from the base of the cliff. Great. Right. Then the ball launcher launches, say same ball launcher, same launching speed. I think those could be reasonable implications. Okay. Horizontally off a cliff. Ooh, with 3 times the height. Where does this ball land from the base of the cliff? So I want to look at this maybe 3 different perspectives. One is to just draw it out. And then, so this is number 6 on your quiz. Right, one is just draw it out. And then we'll do solve in terms of variables. Then we'll solve with a numerical example. And they should all tell the same story. So say I have a 15 centimeter tall cliff, at least 15 centimeters on my paper. Maybe that could be the tall cliff. Okay, so I guess the short cliff would be 1/3 of that. So here, 5 centimeters. There you go. There is a to scale accurate representation of these side by side. Oh, whoops. Zoom out where you guys can see this better. There you go. All right. There you go. So there could be my short cliff, there could be my tall cliff. My short cliff, maybe in terms of variables, I could just call height h, and then the tall cliff could be 3h. Right? H and 3h. Like I said that. All right. And later on, I'll go back and I'll put in some numbers. So here, maybe I'll switch in color, just say that later on. I can make up anything. Can I make up anything? Anything at all? Could I do like, I don't know, 10 meters and 30 meters, for example? Right, I'll put that in parentheses because later on, go solve that specific area. But you can make up any numbers, and proportionally where it lands should be the same proportion, right? All right. So let's throw a little launcher up here, blast and horizontal. Hey, just like you guys did on lab the other day, right? Okay, so I'll launch this ball at some blast speed. I'll call it v sub x because I'm launching it horizontally. So the horizontal component velocity, but it's all the way across. Okay. And it's going to go maybe land like there, for example. I'm going to call that distance x, right? X to right there. Okay. Now, guys, what shape is that right there? What shape is that dashed path? It is part of a parabola, isn't it? Hey, when this launcher also launches with the exact same speed, say v sub x, right? Oh, here, okay. Is that also going to be a parabola shape? Parabola shape, right? It's going to be the exact same shape parabola, just extended, right? I mean, it's the same speed, it's the same gravity field, it's the same. right? I'm just gonna kind of eyeball this, and I guess it's probably right about there-ish, right? Okay. So in fact, if I drew this exactly right, I think I got pretty close. Right? If I take this shape and I slide it up, could it exactly overlay during that first part and right there? Yeah, I think this part and this part should be like copy pasted exactly. They could exactly overlay. Of course, this one keeps on going, right? And the question is, what is this distance right here? Okay. Okay. Now, you guys have the answer circled in front of you. Does it say 1.73 times x? Right? Which is like the square root of 3 times x. So I'm going to make the claim the square root of 3 times x. I could call it, or I could call it d or something, right? Say, what is d in terms of x? How about that? What is d in terms of x? I'm going to make the claim that d is square root of 3 times x. Square root of 3 is 1.73. Okay. Right, so let's see. All right. Solve in terms of, so there's maybe the solution just looking at the picture. It's like, okay, I can kind of believe that's true looking at this parabolas. Okay. Let's solve in terms of variables. So in terms of variables, okay, I could have, let's do the short cliff and the tall cliff. Right. So, yeah, short cliff, some height h, and tall cliff, height 3h. Right. So, these projectiles, if you want to figure out like where does it land horizontally, first you have to figure out something about its vertical motion, right? Which is tied to the height of the cliffs, right? How much wood it takes to reach the ground. Guys, what's the connecting variable? Time. Yeah, right. Guys, however much time I have to solve for time. You guys saw lots of projectiles in this class, and yeah, if you want to switch from say vertical to horizontal motion, yeah, the connecting variable is going to be how much time. Ooh. So how much time does it take to fall some distance? How much time does it take to fall some distance? Which kinematic formula does it sound like? First, second, or the third? First one. Yeah, the first one is the only one that deals with both distance and time. Right now, I can do a simplified version of the first. Here's the full first kinematic formula. X equals v naught t plus 1/2 at squared. Now that's really generic. Right? Oh, but maybe I don't need all of that. Maybe I want to change this general displacement to like a height, like h or y or some version of that. Great. Okay. Great. Guys, when you blast something straight horizontally, throw something straight horizontally, what is its initial vertical component of velocity? Zero. Okay. Right. Guys, does this have the same vertical motion as if you just like dropped it off the edge, like bowling ball, say cannonball just goes rolling off the edge, they hit the ground at the same time? Exact same vertical motion. So for this v naught, is that the blast speed or is that zero? That's zero in a vertical context. So vertically, I'm going to change this general displacement to height for the short cliff h. Right? And this v naught is just zero vertically, so it's just 1/2, and then instead of a, I could call it g for gravity field of the planet, and t for the short cliff squared. Be like that, right? Rearrange this times 2 divided by g, 2h on g equals t short squared. Therefore, t short cliff is, well, square root of that, 2h on g. Okay. Hey, that's your reaction time lab, isn't it? Reaction time lab, right? Of course, if this was a AP pre-response question, they would want to see all these steps right now. So, but you guys have done this several times so far. Okay. All right, for the tall cliff, the only difference is this h becomes 3h. Oh, of course, I'm solving for a different time. It takes a different time. So 3h is 1/2 g t tall cliff squared. Right. Rearrange that. 2 times 3 is now 6. So 6, oops, sorry, 6h on g equals t tall squared, square root both sides, t tall equals square root of 6h on g. Something like that. That's true? Right. Right. Oh, or if you like it, if you just solved it like in general like this, right? Short cliff could just be in general. Right? And you have 3 times the height of the cliff. You could kind of cut straight to the step. I mean, probably for AP, you want to write all this out. Okay, you guys get that? Okay. Right. Oh, but the question isn't how much time does it take. It's where does it land? So now let's switch over horizontal because all this is vertical motion. This is all vertical. Let's switch over horizontal. So where does it land? X. Could that just be v sub x times t? Right? Here's t short. I can substitute this expression bing, right in there. Okay. So where it lands x is equal to, well, the blast speed horizontal times square root 2h on g. Okay, I can do the same thing over here. So this is all, now we're doing horizontal abbreviation. Okay, you do the same thing over here. Here's vertical, okay, and then horizontal. I was calling that D, like where does it land? D, right? Okay. So that could be the same blast speed, it's the same launcher, but now times T tau, right? Which is going to be the squared expression 6h on G, like that. Right. So here's horizontal. Right. Now, if you want to compare these two, say what is D in terms of X, right? Maybe you can think of it like a ratio, right? Like what is the ratio of D over X, right? Again, you have the circled answer in front of you. I'm making the claim it's the square root of 3. Let's see how true that is. Okay. So what is D compared to X? Well, it's this expression, the blast speed times square root 6h on G over this distance, which is the blast speed times square root 2h on G, something like that. Right. What cancels? The blast speed cancel. So as long as you're using the same blaster, then the proportionally land the same distance away. The gravity field planet. So it'll land at different locations on different planets, but the proportional answer again doesn't change. The specific height of the cliff also doesn't matter as long as you scale it by factor 3. So this works out to be, what's this? The square root of 6 divided by the square root of 2. Right? Square root of 6 is square root of 3 times 2. Works out to be the square root of 3. Right? So the ratio of those cliff heights is the square root of 3. Right? And then you can cross multiply the original landing distance. D equals square root of 3 times x. Okay. That's what I did. Okay. Now, that's in terms of variables, which, again, it's a good skill, a good tool for your toolkit to be able to do. Okay. Let's do a numerical example. Let's say I had cliff heights 10 meters and 30 meters. Let me go back and add one more detail. Let's get a blast speed, which is, I'll just make up whatever. How about 20 meters per second? Just make something crazy up. Okay. And, let's throw in a gravity field too. Let's call it 10 meters per second squared down. All right, so we're on Earth. So why not? It's a good comment. Okay. So we got all those details. Let's try it with the numerical, because you could have made up any set of numbers, and I guarantee that we're going to get this ratio of distances is still square root of 3. Okay. All right, let's see if it's true. So to fall 10 meters versus 30 meters, how much time? So, well, here, I'll kind of cut to, I did some work already. I got this square root 2h on G expression. Let's try this out. So for the short cliff, here, let's say G in general. T in general is square root 2h on G. We already did that work, so I'm just skipping a few steps here. Okay. So T for the short cliff is square root 2. I got a 10 meter tall cliff and a 10 meter per second squared gravity field. That's like square root of 2 is 1.414, I think, seconds, something like that. How about T for the tall cliff? All right, that's square root. I got a 2. Now the tall cliff was 30 meters, but it's the same gravity field. 10 meters per second square. Oh, let me extend that square root a little bit. Okay. Just make sure your square root extends over higher inside expression. Square root of 6. What is the square root of 6? That one I don't know. 2.449 seconds. Okay, so that many seconds, that many seconds. Okay, so now where does it land? Horizontally. This is all vertical. Vertical, did that. Okay, now horizontal motion. I'll call x for the short cliff equals the, well, here, just in general, it's dx times t. Okay, so for the short cliff, it'd be, what did I say for the blast speed? Oh, yeah, 20 meters per second. Yeah, all right, there you go. Right. Yeah, so just made up that number. Let's go 20 meters per second. For now, the fall time for the short was 1.414 seconds, or you could do the whole square root of 2 if you like. Okay. So what is that? What is 20 root 2 is 28.28, and that would be meters. Right? Seconds cancels, distance is in meters. All good. Now, distance away for the tall cliff, I've been calling that D, so it's being redundant with the subscripts, whatever. Okay. It's the same blast speed, 20 meters per second. But now it's for this new time, because the taller cliff takes more time. Seconds goes away. what is 20 times the square root of 6? That is 48.990 meters. Okay. So finally, what is D compared to X? That's 48.99 meters compared to 28.28 meters. 48.99 over 28.28 is 1.73. There you go. And then you can cross multiply the x if you like. D equals 1.73x. There you go. All right, so there's a bunch of different perspectives, different ways to go about it. Okay. One of the things to keep telling you guys is if you're ever asked a question in terms of variables and you're like really stuck, like, I really need some numbers. If something works in general for any set of variables, you could make up any set of numbers. It's still going to work. So I'm going to give you the same answer. All right, you guys good? All right. I got okay. Next on my agenda, we're gonna solve this Atwood right here. So yesterday you guys had exactly the setup. Right? Here, I just made up some numbers. Suppose you got 2 kilograms versus 3 kilograms. What's the acceleration of that system, and what's the tension in the string? Go ahead. Solving this right here. Oh, you know what? Backtrack a couple minutes here. You guys do know you had a poster for this too, right? For last instance from the YouTube clip, right? So there you go. That's kind of what we just did. All right. That's good. Which is different than it's different than last speed from YouTube clip. Right? Some parts that are the same, some parts are a little different. Okay, so we're going on to Atwoods now. It's Atwood time. All right, who solved? What is the acceleration of the system? Who knows that one? Acceleration. What'd you get? You got what? 0.2. Huh. I think it's faster than that. Oh. Okay. All right. So here, I'll start walking through this one. Okay, you guys know it's 2 kilograms versus 3 kilograms for a classic Atwood, right? There's your classic Atwood. I got 2 versus 3 kilograms, right? So yesterday I took the first about 20 minutes of class to debrief this, right? So I took you guys through that. Okay. Now this is really similar thought process. It has a little bit different type solution because it's a little bit different setup, right? But here, I'll walk you guys through this. So in the pink box, I have just very generic Newton's second law of motion, right? Just like for this one, that looks identical, right? Okay, so that's the same. Okay. It works out a little bit differently. Now, I like to do what AP calls a whole system approach, which is to say, treating this as one giant system. These 2 different weights are competing clockwise versus counterclockwise. So I just think of it that way, and this pulley is held in place. Okay. Okay. So from that point of view, the net force driving clockwise versus counterclockwise, you have to take a difference in weights. And then the total inertia they moved around, the total mass is just the sum of the masses. Right? And that's the answer. That's the answer right there. Yesterday, when you guys turned in your lab, if you turned in that right there as the answer, then that's exactly what I was looking for. Okay? Now, if you're asked the follow-up question, what is the tension in the string, which I did also ask, right? Then I would go an extra step, say, well, you could pick either block, and set up either this green equation or this green equation. Pick your favorite. It doesn't matter which one you pick because they'll both tell you the same tension force. You can solve the tension either way. Right? Also, like yesterday, I mentioned this too, mentioned this again for this one, is a lot of textbooks, a lot of instructors like to solve it backwards of how I usually solve it. They'll actually start with these 2 green equations as a system of equations. And if you know what the masses are, you know the gravity field, and you keep a track, you would know everything except for, of course, the tension force, but also the acceleration if you start with these 2. That would be a system of equations, 2 equations and 2 unknowns, which you could maybe use as a substitution to solve for, right? Or elimination if you like elimination, or a matrix if you like matrix. Right? So pick your favorite math method. Right? Right. So let's do that. All right. So I got 2 kilograms versus 3 kilograms. About 3 kg right here. Boss guy 2 kg right here. right, got a fixed in place pulley, attached to the ceiling. Okay. All right, let's get some forces. So, guys, how much weight is this right here? How many newtons is that? About 20 newtons, about usually round to, right? Right, 1 kilogram weighs 10 newtons, and so on. Right. How much does this guy weigh right here? 30 newtons. So, oh, look, I made it a little longer. 30 newtons. If I try to keep it proportional, you guys think that's about 1.5 times that? Pretty close. I was trying to make. Right. Now, are those all the external forces I care about? I think so. Right. So this pulley, of course, being held in place, and not really. Oops, that's what I just want to see what's driving the motion. Right. I think those are all the external forces that I care about to be able to solve the puzzle. Right. Right. Now later on, there's a question about tension. Let's go ahead and throw tension in here. Right. Which if you're doing system of equations, maybe you want this anyway. Is this being pulled up with some tension? Is this being pulled up with some tension? Now, if I draw these tensions exactly right, I think this should be like a Goldilocks force. Let's say it should be like the medium-sized force. You guys think the tension should be more than 20 newtons, so it's overall driving the small block up? And it's the same tension force over here, but smaller than 30 newtons. I'll label this F sub T for tension force. You can label it capital T if you like, right? But we don't know what that is yet. But I do know it's bounded between 20 and 30 newtons. Has to be more than 20 newtons so there's a net force driving this up, and less than 30 newtons so that there's an overall net force driving this one down. Because it's going to overall move clockwise, you guys think? All right. So let's try my my whole systems approach here, which I usually do. Net force over total mass. So Newton's second law of motion. Acceleration is, here I'll even write that out. Net force, sum of forces over total mass. All right. So guys, what's the net force? 10 newtons. There you go. 10 newtons net force. Driving how much total mass? 5 kilograms. Aha. Okay. So I have 10 newtons driving 5 kilograms. Does that look like 2 meters per second squared? Okay. And you guys didn't forget the unit too, right? You guys have 2 meters per second squared? Something like that? Okay. Yeah, I think that looks reasonable because what's the boundary conditions for any atwood on Earth? It's always going to be between what and what? 0 and 10 meters per second squared. If they were the same mass, it'd be 0. If you put all the weight on one side, it'd be pure free fall, 10 meters per second squared. Right? Yeah, and this is okay. This looks reasonable. Okay. Right. Follow-up question: what could be the tension in the string? Now, I'm making the claim that it doesn't matter which of these Green equations you use; they'll give you the same tension. Let's say that's true. Let's do it both ways. And of course, if you wanted to, you could actually start with these two equations, but I'll just bring them in right now, one at a time. Right here. Oh, I think I got enough room to split my paper right here. Maybe I'll solve it one way and solve another way. Right? So from the point of view of the 2 kilogram block, so I'll put 2 kg block here, and then I'll put 3 kg block over here. How about that? I think I can fit that on my page. It's nice if I can fit it all on one page. That's nice, right? All right, so let's do Newton's second law of motion as it applies just to this block. Okay, so I'll do acceleration is net force on mass. Okay. All right, but net force, could that be the tension force pulling up minus the weight pulling down, acting on a 2 kilogram mass? Okay. Oh, and I know what the acceleration is. That's 2 meters per second squared, isn't it? Right? So, okay, you guys see that? So in general, it's net force over total mass. And I already saw for acceleration from the whole system approach. So I know that's 2 meters per second squared. Okay, I multiply 2 kilograms times 2 meters per second squared. Guys, what's 2 times 2? 4. And the unit is what? 4 what? What's kilogram meter per second squared? Newtons. So that's 4 newtons equals the tension force I'm solving for minus 20 newtons. Add that over. Tension force is 24 newtons, looks like, from that point of view. Okay, let's just focus on this left block, this 2 kilogram block. Okay. Oh yeah, remember a few minutes ago I was saying the tension force, I was calling it like the Goldilocks force. It's the middle size force. It says somewhere between 20 and 30 newtons to make this thing accelerate that way. Yeah, that looks about right. Okay. All right. Let's see if I'm getting the same thing, just honed in on the 3 kilogram block. So Newton's second law of motion, acceleration is net force, which maybe I'll have down as the positive direction for this one. So I'll do 30 newtons minus the tension. so I can keep the acceleration constant and be, sorry, positive acceleration. It's also constant, but it's positive. Okay, so that net force divided by 3 kilograms mass, and that has to come out to, of course, 2 meters per second squared. Right? If down is positive, looks like over here maybe up is positive, maybe here down is positive. So I think it's easier to work that way. Okay, you guys see how to set that up? All right. Cross multiply 3 kilograms. Guys, what's 2 meters per second squared times 3 kilograms? 6 newtons. That's exactly what I was looking for. A number in a unit, 6 newtons. And that's 30 newtons minus the tension force. You can do a little algebra shuffle, add this, subtract that. Hey, look, you're getting the exact same thing. Exact same thing. Boom, boom. 24 newtons. Of course, it had to be the same thing. I want tension in that string. Guys good? All right. Ba-boom, ba-boom. Let's see what next. All right. You guys ready for puzzles? Puzzle. Oh, sorry. No, I'm not ready because there is another detail I want to show you guys. Okay. You guys remember these elevators? Right. And there's actually this proof too. It's really good to be able to do this proof. Yeah. All right. So be able to do this proof. It's actually a pretty good chance that this could be a free response question on the AP exam, right? Or it's got to show up somewhere. Right. They might fully expect you to write out this whole thing as a free response question. But this is for an upward accelerating elevator. Hey, upward accelerating elevator. Could that be like this one right here? Upward accelerating, right? And if you follow the proof, at the end you get m times g plus a. Hey, I wonder if that's actually consistent with what we just did. That's what I also wanted to do. That's why I like that poster out. Okay, let's try this out. Right, so let's try it. So I got m times g plus a. So m 2 kilograms times open parenthesis g 10 meters per second squared plus a is 2. Right, let's see what this is. Right, guys, if this method works, if I treat this like an upward accelerating elevator, it should give me the tension is 24 newtons. Let's see if it does. Hey, it's 24 newtons. Right, and this one right here is kind of like a downward accelerating elevator. So it's m times g minus a. Let's see if that also works. So now I got 3 kilograms times open parenthesis g minus a's. Right. Hey, it's still 24 newtons. Right, now that's a nice shortcut. If you have a multiple choice question on the AP exam, maybe you could file away that as a shortcut, right? Elevator physics, it could help, right? Right. So here, so in summary, if you have a multiple choice question, if you have these memorized, which I think is reasonable, you could probably solve elevators really fast. If it's a free response question, make sure you know the entire proof because they'll want to see every step. Okay. All right, chapter 4 puzzles time. Puzzles time. Check out. All right, so I got on right here. Okay. So I think the other day we were more focused on the warm-ups, and I stopped before we got to the Atwoods because I wanted you guys to do the lab version first, right? Right. So over here. Yeah, let's go through the circled ones at least. I'll get you guys as far as I can through the circled ones. I want to do the same thing I did the other day, which is pull up the solutions, show you how to think about these, and then ideally you pull out a blank piece of paper and solve them from scratch. And if you can do it, then that is awesome. You're good to go. And if you really struggle, then you know that too. Right. So the first one is circled was number 7. Just kind of focus on those. If you need extra practice, of course, you can focus on the other ones too. Oh, this looks like elevator physics. Is that elevator physics? Yep. 75 kilogram man standing in an elevator. The scale rate's 825 newtons. Ooh. So it's shown a super heavy. What's the acceleration of the elevator? Hey, that's kind of what we just did, but maybe sort of backwards. Right. So here you go. Yeah, again, guys, that proof on that poster that I was just showing you guys with the elevator accelerating upward, that's exactly what this question is. See if you can, for sure, pull out a blank piece of paper and solve this without any help and get to exactly the answer that I got there. Boom, boom. So we basically just covered that one. Number 10 is the next one I circled. Okay, which I also put on that page right there. We got okay, when you see a 5-gram bullet, if you're going plugging and chugging in the calculator, are you going to plug in 5 for the mass? 5-gram bullet? Do you plug in 5 for the mass? No. Why? Why not? Needs to be in kilograms. Guys, remember, kilogram is the base SI unit. That's what's going to be consistent with all the equations. So 5 grams, how many kilograms is that? Yeah, so it's a factor of 1,000, right? So yeah, here we go. I wrote right here. You guys see 0.005 kilograms for the mass. You guys see that? Okay. Now it shows up later on in the proof. Looks like it did kinematic first, and then when I skipped over to dynamics, yeah, for the mass, make sure it's in kilograms. What else I got here? I'm reading off the paper. speed of 320 meters per second, say if it started from rest. And they also give you the length of the barrel rifle. You guys remember that poster that was treating acceleration as a bridge variable? You guys remember that? Right, that's exactly what it did right here. So they gave you 3 kinematic variables: starts from rest, length of the barrel, and then the final speed of the bullet. Boom, boom, boom. You can solve for the acceleration. There's your bridge variable right there. We got crazy number of meters per second squared, right? Then you can do dynamics. Well, if this was the mass that was being accelerated, what force was required? Boom, boom. Part 1, part 2. All right, next one. Ooh, number 15. All right, here we go. Number 15. I'll give you guys a heads up. I shouldn't tell you guys this, but I just wrote your quiz last night. There is a quiz question that's pretty similar to this one. All right, so here we got a ball bouncing off the ground. They told you the height drop, the mass of the ball, the rebound height, and one more detail is they told you the time of the bounce, which is a tiny. I put delta t like a time interval. They said 2 milliseconds. Now, 2 milliseconds, can you convert that to seconds? 0.002 seconds, right? Also, gravity is implied. Whoops, so I threw that in there too. Almost forgot about gravity field, right? Because assuming you're on Earth, that matters too, right? They work out a little bit different on different planets, right? So they phrased the question. They said, what is the average force exerted on the ball? I'm going to add to that a little bit. I'm going to say average net force. Here's why. I drew it in pinky right here. Maybe this is overthinking a little bit, but maybe it kind of matters, right? At the point that the ball is boing rebounding off the floor, there's actually 2 forces on it. There's this normal force from the floor, and there's also its weight. And if you want to say what's changing is motion, that's really the difference between those forces, which is a net force. Although it probably wouldn't make too much of a difference because this force ends up being, guys, look at the answer. I mean, 11,000 newtons. That ends up being so huge compared to the weight of the ball anyway, that even if you forgot that detail, it probably wouldn't matter, right? Just proportionally, right? But if it did, then it's like, okay, right. All right, but really average net force, right? If you want to be kind of technical about it. Right, so guys, if you know the height drop, can you solve for the crash speed? Hey, look at that, it's square root 2gh. Start with the third kinematic formula if you have to prove that, right? And then you can solve for b crash, right? But this is something that you guys have seen so many times in this class. If you know the height of a cliff, you drop a ball, what's the crash speed? It's always square root 2gh if you drop it, right? And then the rebound height, it's the same idea, it's just square root 2gh the other way, right? For that rebound speed, right? So it's going to crash in the ground some speed, it's going to rebound some speed. Now, guys, if it's bouncing off the ground, right? If I got 24 meters per second crash and 19 meters per second rebound, right? What is the change in velocity? And don't say 5, as if you're going from down to up. If you're reversing direction, do I really have to treat this as a velocity as maybe like 24 minus negative 19, right? 24 minus negative 19. You guys get that? Right? So, okay, I did that down here. Okay. So guess here you're basically going to add the magnitudes, because if you reverse direction, it's like subtracting a negative. You guys see that? Right? It's one of those little details that ends up being really important to the answer. Okay. Right. And then it ultimately feeds into Newton's second law of motion. It's like so many of these do. F equals ma. Right? I know the mass of the ball that's being accelerated. I know the change of velocity. And I also know the time interval this happened, because it's that crash time, that boing was 2 milliseconds. Okay. Put that in seconds. Okay. And then you can solve it. Okay. Again, see if you can solve this one completely from scratch on a blank piece of paper. If you get the same answer I got, you're good to go. All right. Next one queued up, number 19. Let's take a look at, where is 19? This one with the bird feeder. Here it is. Here it is. Right. There's a bird feeder. They tell you the weight of the bird feeder, I think, is 150. Yeah, 150 newtons. Right. Now, guys, side thought here. If the weight is 150 newtons, what's the mass equal to? About 15 kilograms. 15 kilograms. Right. A lot of times they'll tell you mass is 15 kilograms, and you have to figure out, oh, the weight's 150 newtons. Right. If this was accelerating, you would definitely want to know the mass. Although this is static, so you don't have to worry about maybe Newton's second law of motion so much, because it's not actually accelerating, it's just static. Anyway, that's just a little side thought, right? Okay, so if you see like the same type question, but they give you the mass, you have to do that extra step of solving for the weight first. They gave you the weight. Okay, we're good to go. Okay. All right, so what I got here? Okay, I got the weight pulling straight down. I got this tension up to the left. I got this tension up to the right. You know what? I do have a poster exactly for this situation. So I can dig this up real fast. I got it. Aha, right here. Right here. I switched my screen. back over. We'll take a look at this. Okay, so I got two variations on it. Let me start with the simpler type one. Okay. You guys remember your spring scale lab? This is one of the mini labs you guys did. Right? So something like this, right? Right. So yeah, weight down, I got a couple spring forces. Now, if it's all symmetrical like this, then spring forces are the same, but simplifies it a little bit, right? But here's the guiding principle, which is going to be the same regardless, right? Is if you introduce a Cartesian system and you take your diagonal forces and you break them into components. Notice I dashed the components. You guys see that? That horizontally, everything has to zero out. Let's say this one pulls right as much as this one pulls left. And vertically, everything zeroes out. So these two are pulling up as much as the weight is pulling down. You see that? Right? Now, let's make this a little bit more complex. What if it's not symmetrical like that? Right. Now we got something that looks more like this bird feeder. Now, it's the same guiding principle, though. Same guiding principle. Okay, introduce Cartesian system. Looks like the weight's already vertical. Leave that guy alone. But these diagonals, I can break into components. And horizontally, everything zeroes out. And vertically, everything zeroes out. Boom, boom. Right? So we got some sine and cosine. We got an alpha and a beta. But it just follows those guiding principles. Okay? Right? So everything zeroes out along each axis. You guys got that? Right? All right. So with that, if you get that, then you'll see everything falls out right here. Right? So now I don't know what is tension left, and I don't know what is tension right. I call it TL and TR, right? Tension left, tension right. Right. So those are unknown variables, but they did give you these angles. So it could apply sine and cosine, and I did that right here. So cosine of 60 degrees, for example, is 1/2, right? And cosine of 30 degrees is square root 3 over 2. Okay, I filled in all of those. I put the fraction form. Okay, so we got the fractions. Right. Right. Now, guess see what I circled right here? I starred them. Starred this one. Starred this one. The sum of the forces horizontally goes to 0. The sum of the forces vertically goes to 0. And then I just created a system of equations, and I labeled it system of equations. It's two equations, two unknowns. Your two unknowns are what is tension left and tension right. Okay? Right. And your equations are horizontal and vertical. So horizontally, looks like, so sum of the forces horizontal goes to 0. So root 3 over 2 times tension right, that's from cosine of 30 degrees. Right? That's pulling to the right. And then 1/2 tension to the left, that comes from cosine of 60 degrees. That zeroes out. Okay, you guys get that? Right and left zero out. Right. And then the sum of the forces vertically also zeroes out. That's your second equation. So this one pulling up, this one pulling up, the weight pulling down, and you know the weight down is 150 newtons. They gave you that exactly. That also zeroes out. You have a system of equations, two unknowns. Can you guys solve a system of equations? Right? Because that's all the rest of this is. Right? Once you got the setup, everything else is good to go. Right? So that's all I did for the rest of this is I just did some algebra. Right? So I did a little dashed arrows to show you like what I'm substituting where. Right? But those are the answers I got. Okay. All right, guys good? All right. All right, so it's a specific setup and followed by a bunch of algebra. All right, next one is circled is number 28, which is you know what? That's a little fancy looking at wood. I'm gonna skip on to 36 and 38 actually, because this one's a little bit fancier. Let's see. Oh, look, this looks like elevator physics going on. Right. Yeah, you guys see 28, it's an incline in and outward combined. You guys see that? Right. Maybe I shouldn't tell you guys this either, but on the upcoming quiz, there's one's kind of like this, right? It's an incline and outward, it's all put together. Right. But let's skip to, okay, there's 36. Here's your modified Atwood. That's what you guys did back on Friday. Right. So if you're given, what exactly did they give you? Let me make sure. They normally give you the masses. Yeah, they gave you the masses. This is a frictionless horizontal table, just like you guys had on Friday. Find the acceleration, find the tension. Okay, that's exactly what you guys did on Friday. Boom, boom. Okay, for number 36. It's like Friday's lab. Then number 38. Hey, this is okay. Well, it's a classic double elevator outlet. I didn't draw the picture, but it's what we did this morning. It's what you guys did yesterday. Number 38 is just that. Okay, guys good? All right, now I can go back to 28, which is a little bit more complex. Okay, we got an incline and an outward combined. Okay, so I'm looking at each block. Oh, now again, I got an option of how exactly approach this. You could solve this from a whole systems point of view. You could just solve this with a system of equations. Two different approaches. They'll give you the same answers regardless of how you do it. Okay, and the two classic questions are: what's the acceleration and what's the tension in the string? So it looks like I did whole systems because I solved for acceleration first, did it this way. Okay. Make a free body diagram for each block. I see this 10 kilogram block. Oh, it looks like it used 9.8 meters per second squared for gravity, got 98 Newton weight, right? It's got a tension holding it back this way. Guys, is this tension pulling up the same as this tension pulling up to the left? That's the same tension. That's a good assumption, right? They said a frictionless surface for this one. So the other force, this has a weight pulling down, has a normal force up to the right. Notice I introduced a Cartesian system and I dashed that off in blue ink. And then I broke this weight into components. I did all that. They gave you 40 degrees. So you can put that in there. You can solve for these numerically. They gave you the mass, you can solve for the weight. They gave you the angle, you can solve for this weight component. You guys got all that? Okay. All right. And now from a whole system approach, here's what I'm thinking. This component right here, which I found out was 31.5 newtons, is pulling the whole system clockwise. It's trying to make this wheel turn clockwise. Right? This over here on the left side, just the full weight, 98 newtons, is trying to make it go counterclockwise. It's a competition between this force and this force. That's it. Between 31 newtons and 98 newtons. You guys see it? It's a competition between those two. Guys, who's going to win? 98 newtons or 31 newtons? 98. So you guys see the whole thing's going to definitely turn counterclockwise, right? Okay. Right. So, hey, that's what I did right here. Newton's second law of motion. That force versus that force. Subtract them. And then divide by, here's the total mass. Boom, boom. There's the acceleration. You guys got that? Right. Right. Then, if you want to solve for tension, either focus on this block or this block. And I did it both ways. Because you don't have to do it both ways, but you can pick either way. I got the same answer either way. Just focus on one block or the other block. Okay. Solve for the tension. All right. What are we doing here? You know what? Since we got about 5 or 6 minutes left, I think a good use of time is I'm going to go ahead and go through some more of these solutions just up here like this. And hopefully pick another day where I can give you guys some class time and I can walk around and help you guys. Right? That's what I'm thinking. Of course, these are all going to be due on Monday, just once I circle. All right, here. I want to look at number 54. You guys see 54? Okay, no, I did not circle this one. But I'll tell you guys what. This is actually a little bit closer to the quiz question I'm going to ask you guys. Okay? Because number 54 looks like the one we just did, except it also has a little bit of friction. Guys, a little bit of friction. You guys see I drew a friction force there? Now, guys, the tricky thing about introducing friction to this incline Atwood is, do you have to know which direction for sure the blocks are sliding for this one? You do. Here, guys, here's why. Because whichever way the blocks are sliding, which way does friction force point? The opposite way. Okay. If you get the direction wrong, you're going to get the friction force wrong, and it throws the whole thing off. Okay. Now, when I was designing your quiz, I tried to make it pretty obvious which way it's going to accelerate. I say, okay, well, if this one's heavier and it's also hanging vertical, that's probably going to go that way, kind of thing. Right. Right. But at least make a good guess. Make a good educated guess. Right? And I think you guys could probably figure it out on the quiz when you see it. Right. And okay, so whichever way it's sliding, friction force is going to oppose that motion. Okay. It's kind of like the one we just looked at with that extra complicating step. Okay, so you give them a bunch of values, masses, the angle, gravity field. Now, this particular question, it looks like they told you how far it slides and how much time. Now, if they told you that, ooh, guys, if it starts from rest and they tell you how far it goes and how much time, could you solve for acceleration? And if you're solving for acceleration, they must have been asking what's the coefficient of friction. Let me go back and read that. Were they asking for that? Find the acceleration, find the tension of the string. Yep, question C is what's the coefficient of friction? And I didn't circle this one, but this is really good practice. By the time you get to part C, they're asking for that. What was the coefficient of friction? Okay. All right, guys get that? Okay. All right. Did check something. All right. Yeah. All right, so there's just a couple other ones that I actually did circle. So let me go hit those, see if I can fit them in before the bell here. So one was 46. Here it is. Hockey puck. You strike a hockey puck. This one was in terms of variables. They gave you no numbers. Right? So you strike a hockey puck. It's some mass. It slides some distance x. And they were asking for, actually, that's what they asked. They were asking for how far does it slide? How far does it slide? Right? No, guys, if there was no friction, how far would it slide? Like infinity? Yeah, it would just keep going around the Earth forever if there was no friction. It would never stop. Right? So the fact that I look for a stopping distance, I bet there has to be some coefficient of friction. Right? This is all in terms of variables. So I did a proof here. See if you can, just like with all these, see if you guys can solve this on a blank piece of paper with no help, right? And if you're really, really stuck, then of course you have all the help you need right here, right? Because it shows exactly step by step how to solve this, right? Question A was what's the acceleration? Oh, guys, notice what variable canceled out on part A? The mass canceled out. Hey, so if you had a light puck versus a heavy puck and suppose they're made of the same materials, should they slide the same distance, given the same initial velocity? Yeah, because they have the same acceleration. So by the time you answer question B, what is the sliding distance? Mass is also not a part of that expression either. Canceled out, right? That's a classic thing to happen in physics. I might replace the puck with a car. Suppose you have a light car versus a heavy car. Same thing. You should expect the mass to cancel out. You see it happening right here, right? And the last one that I circled is okay. We're back to it's like the bird feeder type question, but it's a traffic light now. We find 59. There, oh, there it is. Okay, it's this one right here. So now it's a traffic light. Actually, this one's even simpler than the bird feeder because look, it's symmetrical, right? So all the angles are same left and right. Okay, so they asked questions about the weight of the light. Okay, they gave you the tensions and asked for the weight. All right, so a little bit backwards type question. All right, so there you go. There's a complete coverage of those. Yeah, so we got 3 days left this week. I'd like to make at least one of those days a day mostly to give you guys time in class to work on these. And then, yeah, of course, whatever you don't finish by the weekend, you guys can turn in on Monday. That's our wrap on today.